Hello everyone. I record this series of course to prepare the rocket competition team of Fengyang University. I will introduce the rocket engineering, including very fundamental concept and basic knowledge and some part of a simulation. Because I lack of the time to prepare all classes, all course materials, so I will record it in a random topic. So today I would like to talk about the dynamic pressure. Before that, I would like to review the static pressure. For example, there is a point mass in the air. We all know that the air has a lot of air molecules. They generate pressures on this object. If we say it has object with a mass n, all right. And the pressure, static pressure, defines as the force the air molecule act on it divided by A, the area, the surface area. Normally in the sea level, the object will has the static pressure about 180 m. All right, that is most common knowledge. Okay. And then let us review the momentum conservation. The concept of this is there is no mass can be created or destroyed. For example, if we consider this small box, and there are some fluid molecules flows into this box and flows out, and there are some molecules, for example, fluid molecules stay in. So the number of the fluid molecules stayed in equals to the numbers flows out minus flows in. Right, I show over here if you want to see the equations. So this variant, we call it the control variant, and which you will learn this concept in the fluid dynamics or fluid mechanics. And if we extend this idea, we combine these two concepts together, okay? These two concepts together, we can have a dynamic pressure definition. First, this is the static pressure. Of course, it equals to F over A, the area. And this, let me draw this. Okay, for example, we're in the air now. All right. The amount of air molecules with the mass m, we say it has a total mass capital M, and we measure length of these areas, so this becomes a phylum here, and the acceleration, we all know that F equals to ma. The air molecules act, the force acted by it to this object equals to m times a. This acceleration times the air equals to the velocity if we consider the air is not so huge. Okay. So from all this combination, let us think about the rocket condition. This is a rocket tube, and this is the air molecules. As the rocket fly forward, the molecule will follow the flow streams to generate the pressure on this tube. So if we consider a very small distance it travels, we can write this dynamic equation down to here, because the directions is opposite to each other, and we can have a little bit with a dx, because the molecular has the friction always it generates the pressure on the rocket tube. So we can write this formula down, and we do some simplification and we do the integration. We can have the constant static pressure here times plus rho times v squared over 2, and this is the dynamic pressure, which equals to constant. And this constant is the total pressure of this rocket we made. So we have this definition of the dynamic pressure equals to rho times v squared over 2, and this v means the velocity of the rocket. All right. So basically, we can see that as long as the rocket velocities increase scarcely, we will have greater and greater dynamic pressure. But please note that the air density will reduce along with the altitude. Okay, so there will be a max dynamic mid between the increased greatly velocity of the rocket and the decreased air density. So there will be a maximum value of dynamic pressure. We call it max Q. That's why when you see any kind of a rocket launch, you will notice that there is a small screen information about the velocity, the speed of the rocket, the altitude of the rocket, and they will meet the first point. They say max Q. That means the rocket has the max dynamic pressure now, and all the material, all the structures meet the maximum value of the dynamic pressure. And if it passes this point, then the dynamic pressure will reduce rapidly. So basically the structure will be safely, so we don't have to worry about the material structures problem. So this is what situation you will meet when seeing a rocket launch condition. Okay, so if you really want to do the simulation of this figure, we say the figure 1. Okay, figure 1. No matter what kind of program you use, Python or MATLAB or any kind of a program or language, that's fine. The basic concept I showed here, the flowchart, is I want to do the calculation of dynamic pressure, which equals to the air density times velocity squared over 2. Here we have to note that the rocket velocity basically is a function of thrust and time, and this is a very basic equation that you can use. The thrust minus the drag equals to the force that the rocket has, and divided by m, the mass, equals to the acceleration, and by integrating this, you can have the velocity, of course. Okay, and the second is the air density. The air density is a function of altitude, but we'll know that it will varies with the altitude. And the altitude is basically a function of the velocity of the rocket and the current time. So we have to use the first information we have from this flow chart that we mark it as number 1 to get the information of the velocity of the rocket, to get the information of the altitude of the rocket. Then we can check the table, or we can put the equation. We have an equation here, okay, to calculate the air density, and then we feedback these two information back to your diagram or your model. We can have the dynamic pressure here. So you can try this at home to see if you can plot this figure similar to this figure 1. Okay. So this is about the definition of dynamic pressure of the rocket. Thank you for listening. What follows is the Chinese version. If you don't need to listen to this, you can skip this part. 各位同学，我准备这门课是为了我们逢甲大学的火箭团队莱特10号介绍有关火箭工程的背景知识，一些基本的常识，还有做一些简单的模拟的介绍。那因为没有太多时间做系统性的整理，所以我这边就先以主题式的方式来呈现。那首先我今天要介绍的是动压。在这之前先回顾一下什么是压力，静压。好，在物体在大气中会承受到1大气压的压力，那这个来源是来自于大气中会有很多的空气分子，空气分子产生的压力会等于它的作用力作用在这个东西上面，然后看这个东西的表面积的大小，所以这个是静压。那再来介绍另外一个观念是动量守恒。动量守恒它的核心思想是没有东西，没有物质可以被凭空创造或消失。譬如说这是一个小方块，那这里是流体分子，有多少颗流体分子流进去这个小方块，减掉流出来的数量，就会等于在里面停留的。这个是以后你们上流体力学会学到的重要的核心概念。好，那如果是数学式子的话，我表现在这边。所以呢，这个是能量守恒，动量守恒啊，因为这里质量不只是质量，它还有速度。我刚刚说流进去跟流出来，所以它是一个流体，它是有速度的，所以我们这边都是有速度。那质量乘以速度就是动量。好，我们把上面2个概念加起来的话呢，就成为动压的核心概念了。首先，我回到刚刚的静压的方程式 ，F 除上 A， 那这个 F 就是我在大气中我的大气分子，假设有它们每一颗质量是 m， 好，今天有很多颗，那它整体的质量就是大 M， 好，乘上它们的加速度，这就是力。我将这个表面积，这个东西的表面积，好，乘上一个高度 L， 就会成为一个体积，就变成这个小体积。好，这个以后在流体力学你们会学到，它叫做 control volume， 就是一个控制体积。这个就是大气密度。后面呢，加速度乘上 L。如果这个 L 是一个很小的距离的话呢，就是速度。好，这是简单的表现。 表示。我们把上面的概念延伸下来到火箭上，这是火箭的箭身，火箭朝前的速度 v， 空气迎面而来的速度，空气粒子迎面而来的速度也是 v。我取一个很小很小的区间 dx， 那在这里火箭前往的速度跟空气粒子过来的速度是一样的，那在这边停留的非常短暂的时间，这段距离产生的压力就叫做动压。那因为它这个方向是相反的，所以我有一个负号在这边。那我把这个式子做一个简单的整理一下，就可以做积分，得到这边会有个常数。那因为这个积分这个微分结果是0，所以我积分完会是一个常数。这个常数就是总压 （total pressure）， 它区分为静压。当然我大气压力给它的静压是一定会有的。第二个就是动压，随着我空气粒子移动速度是 v2 平方的时候产生的，这个就叫做动压。OK， 所以这就是动压的来源。好，那原则上火箭的速度越快，我这个动压就越大。可是不要忘记，我的空气密度会随着高度变高而降低，这之前航概有学过。所以两者相遇会有一个最大的动压值，最大动压值我们叫做 max Q， 就如同这张图画的，当我的火箭速度越来越快的时候，我的高度会越来越高，这个时候大气的压力就越来越低。两者交汇的时候会呈现这样的一个曲线，会有一个最大的动压值，我们称之为 max Q。 所以当我们看火箭发射的时候，下面的那个一些提供的观众看的资料当中，除了火箭当下的速度高度以外，它会特别提供一个叫做 max Q， 它通过了一个 max Q， 那个就是指火箭在通过了最大动压这个点。最大动压也就是这个最大的动压值嘛。那如果今天火箭都可以通过这个最大动压值了，那我们就可以不用去担心它接下来结构能不能承受更大的压力，因为接下来这个动压就是不断的降低了，所以基本上就可以说它已经到了安全范围了。所以在看火箭发射的时候，这个动压是非常重要的。那如果同学们想模拟这个图呢，不管你用什么程式语言也好，我这边提供一个简单的flowchart。因为我动压是 ρ 跟 v， 它是两个变数，所以我在做动压计算的时候，我需要这两个资讯。首先，火箭的速度会跟它的推力还有时间有关。那我们这边用简单的一维模拟的model， 火箭的推力减掉它的阻力除上它的质量，就会它的加速度等于它的加速度。这个时候我可以求出加速度，加速度积分就是速度了。那所以我就会有第一个资讯速度。那第二个要知道的是大气压力的密度，大气密度。大气密度是高度的函数，那高度又是火箭速度跟时间的函数，所以我必须要透过这边把火箭速度求出来，然后带到求出来，然后再去做积分，找到当下的高度去对应到当下的大气密度。当然大气密度它是有公式的，或者是要查表也都可以。那如果是写程式的话，我当然会建议写公式上去这公式我们在航概里也有教过。所以把这两者资讯带进去，就会得到动压。那同学们可以写写看这个程式，看画出来的图是不是有这样的趋势。OK， 以上是我们对动压的介绍。